I'm going to push that. Okay, recording right now. Okay. Okay, so I said finding UMP test is about pattern recognition. Read about what you do about your null hypothesis and alternatively. When I say if you're doing simple in null hypothesis versus simple in alternative, and then if you recognize it, then you will know what way you are going to find UMP test, what theory you are going to use. Answer is what? Lehman, Pearson, lemma. And then you are going working on the ratio of two PDF. One is on alternative by the one, right? You are going to working on the two PDFs. Okay, let me take it out because I have condition already. Okay, so you are going to working on a ratio of two PDFs or ratio of two Lagu function. By any means you code it, and then you know that bigger than success. Again, how to find C? Using your size, using your type of error probability to find cutoff C. The same thing as the laboratory test, right? X belongs to rejection region. It's okay. Using that to find C. Okay, and then moving on, what happened to if I do have simple versus composite on one-sided? Okay, in this case would be what kind of theory you are going to use to find the UMP test? The answer is again using Lehman, Pearson, lemma. The reason for that is this rejection region right here. Okay, you don't see theta 1. Okay, again it's in the frequentist approach, we only protecting type 1. Okay, every critical regions was constructed based on type 1 error probabilities. Okay, it's nothing to do of your alternative spaces. Okay, so since the rejection region of UMP test under simple versus simple, it's nothing to do with alternative. So that means every alternative theta 1 right here, every theta 1 bigger than theta 0, you're using the same test, you're using the same rejection region, and every one of them are UMP test for that single point theta 1, such that is the same region is going to be a UMP test for every theta 1 in the H1 in alternative edge. Okay, that's how you find UMP test. And then even further is what right now would become theta smaller than theta 0 is composite versus also alternative is a composite. Alternative is a composite. You might want, because I've heard bird chirping. Okay, so if it's composite versus composite, although actually I want to hear some of you saying something. Well, I just get used to myself talking to a machine right now. Okay, so if the composite versus composite, okay, then what theory are you going to use to find UMP test? The answer is what? Cullen-Rubin theory. Okay, so in order to use current Rubin theory, you need to do two things. One thing is finding a sufficient statistics T. Okay, the second thing is to show that your original PDF, okay, or the PDF of the sufficient statistics has that monotone lag ratio property. Okay, I'm going to make it bigger to run me on this. Okay, then what is the lag ratio property? What is the lag ratio property then? It's actually you're also working on the ratio of two PDFs, and then you are going to show that it's the ratio of two PDF right here. The ratio of two PDF right here is going to be an increasing function of your sufficient statistics. Okay, if you do have theta 1 bigger than theta 0 right here. Okay, so this is mainly testing for hypothesis. I think it's for, let's see. Okay, by any means, you do need to given these conditions and then to see the increasing function of your sufficient statistics. Okay, if you do have that, then we'll test in this. Okay, using current Rubin theory, testing composite versus composite, right? Small equal to. So that means I need to be more rigorous right here. I need to put equal right here. Okay, good. So in this case, so you do find sufficient statistics right here, and then show that you also have MLR properties. Your ratio of two PDF is going to be increasing function of sufficient statistic T. Okay, then such that you could directly using rejection region of T bigger than C to define the UMP test. Okay, again, it's how do I find C? Using that size alpha. Okay, again, it's alpha equals to under null hypothesis. Your null hypothesis what? Under null hypothesis, your null hypothesis is theta smaller than theta 0. Okay, you do need to find what? Supremum. So let me take out this. You do need to find supremum and then theta under null hypothesis. Okay, then have your probability of indicator function, then T bigger than C right here of your rejection region. So no, it's not right here. It's not really that. It's actually is T bigger than C because of expectation of delta. Okay, so that means using that to find a column C, but you do need to evaluate. I keep saying so is you do need to evaluate when does that supremum happen. Okay, and then I also say that it's in some case you just fail to realize how I'm going to evaluate the supremum is. Okay, what do I say? I always said good things always happen in the boundary. Okay, so hopefully you can evaluate. Say you really have no idea how I'm going to evaluate, then just plug in theta equals theta 0. I think 99% you are going to get a right answer. Okay, good. So then, of course, if you do have switch of the direction of the inequality is, for example, your alternative is smaller than, but your null hypothesis is bigger than, okay, kind of switch, right? Switch directions, okay. Then you switch your sign then, right here, okay. Again, it's like I always said that you just follow the direction of the alternative. You will get a right answer of that, okay. So let me say something you might feel confused but it could happen because I really don't know what sufficient statistics are going to find. Okay. Say if you do find your ratio to PDF, okay. If you do find your sufficient statistics and you are very, very sure your ratio of two PDFs is a decreasing function of your sufficient statistics. Okay, I'll say it again, decreasing function. Okay, and you are pretty sure that decreasing function, not increasing function, like this guy said right here. Okay, it could happen. It could happen because sometimes the statistics you are finding, maybe there's a minus term right here, or maybe not. Okay, say if you do have sufficient statistics and you are pretty sure that your ratio is a decreasing function of the sufficient statistics, okay, then it's going to be switch of the signs, which means that even the same hypothesis, if you do find your ratio of two PDF, the decreasing function of sufficient statistics, then everything's going to be switched. Bigger becomes smaller and smaller becomes bigger. That's because you are having MLR as a decreasing function of the sufficient statistics. Okay. Hopefully you don't see that. Okay. Again, it's you can always put minus sign on your statistic become increasing function in some sense. But we see increasing function more often as a function of sufficient statistics. Keep that in mind. Okay. Good. So then I would say even further is what? Even further is this. Okay. Even further is what? So I said, hey, what if your state are actually simple, but versus alternative is actually composite but two-sided? Okay, in this case, the UMP test not always exists. I'm not going to rule anything out of this. Sorry, I would say not always exist. Okay. See, this example is a typical example I talk every year about. Why, in this case, example right here, okay, you won't have your UMP test. Okay, so it's my first time to trying online to talk about this. Hopefully you guys get it. If not, well, let me know. I can find another occasion to explain it to you. But it's not really too easy to get it. Why is the case? Okay, so say if you do have the hypothesis, if x1 to xn, okay, follow normal, say sigma square. Okay, right now sigma square is known quantity, so you don't have to do anything about it. Okay, good. Then you are testing about this, right? You're testing about null hypothesis. They say that equals to 0. Alternative, say that does equal to 0. Okay. More than likely, your critical region is going to look like this. You have your x bar right here, minus 2 theta 0, so 2 theta. Then divided by your standard deviation right here. Then bigger than 1 over 2. Making sense? You have your x bar even bigger, you reject it, or x bar smaller, you reject it. It's a two-sided rejections. Okay. Then I'm going to ask one thing, possibly final. But I think I'll definitely give you that in the homework this week. It'll be homework number 8, if I remember the number correctly. I'm going to ask you, hey, if I give you a rejection region right here, could you draw me a power function? Okay, power function, if you do remember, that is what? probability of theta. Given theta, theta could be null space, could be alternative space, okay? But inside the probability is always your rejection region. It's okay. So this is going to be my power function, and then it's going to be function of theta. So then, based on this, you are going to draw a graph right here, okay? And then tell me what you look like if this is a power function of theta. And then you are going to evaluate, okay? So then you do what? You basically working on the probability inside, right? So I'm going to say that's what x bar minus theta 0 divided by square root of n bigger than z 1 minus r over 2, okay? Or so let me do one thing. I don't want to just make a mess right here. I do want to have a clear picture about my power function. It's how about this? Let's go going on right here. Okay. So right here is what? I do have probability of theta. Okay. One side is the x bar. This is one side. Then or x bar so on and theta 0 divided by. This is the other way around, right? So one side bigger than z 1 minus half over 2. The other side is minus. That means bigger and then smaller. I'm going to reject it. Okay. So theta right here. Because of or, I can write down as plus. And then I do want to jump a little bit because I want to do one thing on a safe space. So what I mean by jump is I want to do right minus x bar bigger than theta 0, then plus z1 alpha over 2 sigma divided by this, then plus probability of x bar smaller than sigma 0 minus quantile sigma squared divided by n. Okay, so nothing but just moving things around to get at two probabilities. Okay, so again, it's because my true theta is theta. Right now, theta not necessarily theta 0. You have got to keep that in mind. So it means true theta is theta. So if I'm to looking for standardized again, I minus theta. Now minus theta 0, then divided by sigma squared divided by. This one is actually z. Okay. If you put not here, it's not necessary z, because you need to know what theta is at. Okay. Yeah. Because I put theta in general, so let's get true z. Okay. So then I do something in the left hand side, I do that thing in the right hand side. So that means theta 0 minus theta divided by sigma squared divided by n. Then plus, right? Oh no, not plus. Minus theta 0 divided by then plus z1 alpha over 2. Okay, so step back to look at minus theta 0. Yes, divided by sigma squared divided by root n. Yes, I think I got it. Should be right. And then this guy right here would be probability x bar minus theta 0, 12. Okay, this guy. Hopefully I got bigger place, but you know what I'm trying to write. So, and then this guy would be theta 0 minus theta again, and then divided by square root of then minus z alpha over 0. Okay, again, I'm creating a normal 0, 1 right here. Good, great. So I think basically that's all we can do. And then we are going to using that two probabilities to evaluate what's going on. For example, first is, if I really having that theta as theta naught right here, okay, which basically means that it's, if my theta is under null space, what happens? Okay, if you're replacing your theta as a theta naught, right here. Okay, say if theta equals theta naught. Okay, so let me write it here. So let me write it here. Okay, say this is A and then this is B. Okay, so if I plug in theta naught right here, so let me take that out first. Take that first. Okay. Theta naught, right? It's then bigger than, right, your z right here, normal 0, 1, then bigger than z half over 2 right here, right? If I plug in theta naught, this guy 0, then that becomes your z bigger than quantity z 1 minus alpha over 2. That means your answer is what? Alpha over 2. So that means A becomes alpha over 2. How about B? Okay, again, this is z, normal 0, 1. You plug in your naught right here. The first one is 0. Then smaller than minus z of power 2 right here. Okay, again, left-hand side smaller, left-hand side smaller. So this guy right here also alpha over 2. So that means your B is alpha over 2 as well. Then A plus B becomes alpha. So that means if theta actually has theta naught right here, then your size is alpha. Okay, good. And then you might imagine when theta getting bigger or getting smaller, okay, at 2 terms, then you start to imagine where your beta theta go, okay? And you know that your beta theta, because of probability, they are not going to be over 1, okay? So 1 will be there, 1 will be beta theta's upper bound, okay? Then you imagine what if theta getting bigger then? If theta getting bigger right here, go to right hand side, okay? Theta getting bigger and bigger and bigger, okay? Then what happened to A and B? This guy, because theta not taking out, okay? So, okay, look at A first right here, okay? Imagine your theta actually going up right here, okay? If your theta going up, you got minus term right here. That means when theta goes to infinity, this minus theta right here, making the first term what? Goes to minus infinity. Making sense? Okay, so that means A would become like what? A would become like probability of Z bigger than what? Bigger than minus infinity when theta keep going. Okay, the whole quantity will go to minus infinity, like right here. Then this guy is not important anymore, right? It's constant. Okay, so that make that it's your A is going to what? Normal 0, 1 bigger than minus infinity is what means this guy is going to 1. That making sense. So that means getting bigger, the whole likelihood function is going to become 1s, like this one, right here. That's A part. Okay. How about B part right here. The theta going to minus infinity. Okay, I'm looking for when theta going to minus infinity. Okay, then look at it right here. Let me take out another necessary notation. So imagine this guy is going to actually keep decreasing because going to minus infinity, mathematically keep decreasing. Okay, and again, there's a minus term right here. If theta going to minus infinity, then the whole term right here become what? Going to become positive infinity. Making sense? And then B become what? B become Z smaller than positive infinity as well. Right? The first term goes to positive infinity. Then minus this guy right here, this guy constant, not important anymore. Okay? So that means again is Z smaller than infinity also is 1. So imagine that it's as soon as theta getting this smaller and smaller, your power is actually increasing. That means the guy right here is so this is a rough, okay, this is rough power function of test it, okay, very rough. I don't have to be precise. And then this guy actually look pretty, right? Size alpha has either bigger or say more power, for example. But why then? Why we cannot have the most powerful on every theta point? Okay, that's a key part. Before I do that, pardon me on this. I'm going to take this guy a little bit out of the shape. So I actually want to do that because later on I want. Oh no, it's still not good. Later I'm going to put another power function on it, and then you'll see. Okay, for example, right here. Okay, of course they will be very balanced. I'm just not good at drawing an iPad right now. Okay, that could be very balanced. Okay, good. So imagine what UMP test is. UMP test basically is what? Uniformly most powerful test. What does a uniformly means? Uniformly means my test is going to be more powerful at every theta point. That means in a whole space at any point in my space, okay, my power curve is going to be the largest among competing ones, okay? Which also means that it's as long as I find single one power curve at one point, which is more powerful than me, then I cannot call my test is a UMP test. Making sense? Okay? Even their power curve is a lousy one. What does that mean by lousy one? Let me give you one. So we are talking about right here is what? The power curve of this test. Okay? This test making sense because it's two-sided test have two tail. But the point is that you cannot stop me to proposing another test. I call it lousy test. What is the lousy test? Is only I using one-sided test. 1 minus alpha, I think. Either way, okay? So the difference between these two tests is, okay, the difference between these two tests is what? The one is I have absolute value right here. That means bigger or smaller, I'm going to reject that null hypothesis. But I can also say, hey, regardless, I only reject it when things are getting bigger. One-sided test. Okay? So again, it's I give you any test. You should be able to draw power function of the test. Making sense? So I give test. So then, yes, of course. Then let's do that, right? Probability of theta. And then x bar minus theta 0. Okay? Bigger than 1 minus alpha right here. Okay? Again, it's over theta, rejection region is my power function. You're actually doing the same thing as we did previously, right? You move x bar bigger than theta 0, then plus z 1 minus alpha, then theta divided by n. Okay? And you do standardization x bar minus theta divided by sigma divided by root n, then bigger than theta 0 minus theta divided by everything look the same, except this guy is z 1 minus alpha, and this guy is z 1 minus alpha over 2. It's okay, good. Say I have that. I do know this guy is normal 0, 1 right here. Okay. Again, you'll do the same thing as the previous one. It's if under null space theta is theta 0, what is the size of my test? Again, you plug in theta 0. The first term right here, 0. Okay. So your power become what? Your power at theta naught become what? Right? Z bigger than z 1 minus alpha. Again, you have a z right here. Okay. Then bigger than z 1 minus alpha. It's a quantile. Your right hand side is what? Is alpha. So it means if I theta is theta naught in null hypothesis, my size is going to become alpha. That means right here, I'm also size alpha test using this test region. Okay, good. Then you are trying to evaluate when theta going up, okay, or goes to positive infinity, which means that it's if my theta going to bigger, okay. Again, the same thing. If my theta getting bigger, or my theta getting smaller, what will happen to this test? Okay, good. Again, it's still similar. If theta getting bigger and bigger, okay, whole thing become minus infinity. Okay, again, z bigger than minus infinity. I'm not going to write it, but maybe I write it. How about that? Maybe that's easier for everyone to see. Bigger than minus infinity. Again, it's going to be 1. That means if it's theta getting bigger, okay, my test is from here, we're going to be 1 as well. Okay. Then how about I say so? Okay, I will just stop right here a little bit. Okay. Let me talk about theta become smaller. It means if theta minus infinity. Okay, what happens? If theta goes to minus infinities right here, okay, let me take out some of that. If theta getting smaller and smaller and reaching the minus infinity, that means the whole thing right here become positive infinity. That means you're talking about z than positive infinity. Okay? Then become what? Become 0. That means imagine this test. If theta getting smaller and smaller, I'm going to having their power curve down here. Okay, so here comes the critical point. Okay, look at real life right here. Basically, it's a power curve. It's a power curve. Is a curve of test, your test. Okay, then compare to a dotted line. Okay, when theta or dotted line of this test region, when theta is smaller here, dotted line, power is actually lousy, right? Going to 0 when theta goes to minus infinity is. That means in the left-hand side of the power curve, real line definitely beat dotted line right here. Beat means that it's the realized power curve is more powerful than the dotted line. Then here comes the tricky part. Why is it tricky? It's, you know what? If you actually compare the real line and dotted line, okay, I've told you that the reality is this dotted line is actually slightly more powerful than the real line. Okay? It's actually comparable, but you may run some kind of data here. Okay? I'm not going to say exactly why one's bigger than the other than say one thing. Okay? So the power curve, because there's some hole in my arguments, I cannot solve in the hole mathematically, so I can say it. Look at this. Okay, so the truth, this is a power curve. Okay, let me write it here. Maybe it's easier to do comparison. Okay. This is the probability of. So let me write it here. I want to write this guy right. We'll be able to see that more clearly. Z bigger than theta 0 minus theta and divided by plus z 1 minus alpha. I tend to write it. Okay. So another one is what? Power function theta equals to probability of z. Okay. Probability theta z. Again, the difference only by z 1 minus alpha over 2. Okay, so tell me, what do you think about which probability would be bigger? Okay, so imagine that these two guys are constant, right? Or fixed values. Well, these two basically is the same thing, so they have the same base. Okay, but one is what? One is this guy is a bigger, smaller quantile. Let me start a little bit. I think one is this guy would have a bigger quantile. This guy would have a smaller sorry about that, reverse. Z 1 minus alpha is smaller quantile. Z 1 minus alpha over 2 is a bigger quantile. Okay? So that means this guy is smaller quantile, right? The probability of Z bigger than some base plus bigger quantile. Maybe you can see this guy really, really close to 0, for example. I just it's actually not zero, but because the theta not necessarily theta zero, but imagine there's some constant right there, okay? So that means it's this probability is z bigger than what? Smaller quantile. The right-hand side probability of smaller quantile is going to be bigger than the probability of this guy is larger quantile. Okay, so it means by a pairwise comparison, I do know this probability bigger than this probability. That means beta star theta is going to be bigger than beta theta. And then I know you have a question about, hey, I got little b right here as a plus. Maybe b is large enough to overcome the inequality. The answer is no, but I cannot evaluate that mathematically to told you why b is not going to be big enough to beat this probability. Okay, so all I'm trying to say is, even the test is lousy, okay, but I do have some area of thetas. My power is slightly larger than your power on that value of theta, which means that you cannot claim U as a UMP test. Making sense? This guy is beta star theta, and this guy real line is beta theta. Okay, so likewise, another lousy test is what? Another lousy test. I can use another side of, which means that it's another lousy test. I mean to say rejection region. Another lousy test would be x bar minus theta 0 sigma secant minus 3. And then smaller than z 1 minus alpha over 2. There's a minus term right here. And it's not alpha over 2, it's alpha. Okay, so another lousy test of this, and then I'm not going to repeat, but you're supposed to know how to draw beta star star theta as a power function. Then it's not really surprising that another lousy test, the power function look like what? Again, when theta getting bigger, the power decreasing. Okay, well, lousy, right? Compared to real life right here, when theta bigger than theta 0, I have no power, whatever. But whenever my theta is smaller than theta 0, my power is actually slightly bigger than U, which is this guy right here, only slightly bigger than U. Okay, so that make the power of your two-sided test, even though it's some kind of powerful in both sides, but it cannot be called UMP test because there's always some lousy test is more powerful than me in some area of theta. Okay, so that conclude about why sometimes your UMP test does not exist whenever you have a two-sided test, like this guy right here. Okay, I cannot rule every two-sided test out, to be honest with you, especially if you have other statistics, things become tricky. But in this kind of normality test right here, okay, z-test or t-test, your two-sided test is not going to be UMP test. Okay, so then that comes down to some kind of step back, which means that I still like my two-sided test. I still like my two-sided test right here. I still like it because it looks like it still have bunch of power in every point of theta. I still like it. Then if that's not UMP test, can I actually limit my class of tests? Among the limit class of tests, my two-sided test is the most powerful. Then it says yes. Then here comes the unbiased test. Okay. So the definition of unbiased test is your sub of power function is going under null space is going to be smaller than inf of your power function in the alternative space. Okay. So look at lousy test. You will see that that kind of lousy test is going to be kicked out of this class. For example, right here. Right. So if my lousy test like this, if this is my lousy test, beta star star is okay. So the supremum, okay, of my now the sub of my power under null space. Right now my null space is single point, right? Theta now only have single point, theta is 0. So there's no supremum sub or inf. Then this is alpha, only single point right here. And then in my alternative space, that means this is my alternative. Okay, so my null, this is my alternative. This is my alternative as well. Okay, on both sides of the null hypothesis, where does that inf come from? The inf actually is what? It's going to become really close to 0 right here, right? The smallest one of my power function is what? Maybe theta goes to infinity. Okay, so right here, which means it's using this kind of criteria, I can rule out that lousy test because my supremum of null hypothesis alpha is bigger than my minimum one of the power in alternative spaces. So this kind of inequality is not satisfied using my lousy test. You guys see that? Okay. So lousy test, this is alpha. This is 0. Okay. Alpha not going to be smaller than 0. So the lousy test will be ruled out. Okay. But the test you are ruled for is what? Is going to be satisfied because in the null space, this guy alpha in null space. And then what happened to that smallest one of the beta of the power under alternative hypothesis, that still alpha, right? Inf, right? This guy, oops, this guy is going to be this beta function right here. Okay, so this is real line right here. Okay, so real line, this guy is the sub of beta theta. That guy also is inf of the beta theta under hypothesis, under alternative spaces. So that kind of two-sided our power function satisfied unbiased test. Okay, good. Then you'll be able to show that that kind of test is going to be most powerful. That kind of test is going to be most powerful among these unbiased tests. Okay, we are not going to go with unbiased tests that much. Okay, in this label. Okay, but in the next year for PhD students in 761, you are going to talk about it a little bit about unbiased tests. Okay, good. So wow, okay, I spent so much time explaining this already. Okay, they're about like maybe 25 minutes away. Okay, so let's talk about famous p-value. Okay, every time I look at this, I'll say, students, you guys have your own version of what p-value is, right? So, I mean, lay languages, how to talk to your friends while you're going to using p-value everywhere. And recently, also p-value become a hot topic because a bunch of people don't like p-value to make decision. Okay, I understand that. Especially if you are patient, then p-value is trash, I think. Okay, so I would let you know why they think this is trash. Okay, good. And actually, I agree with them somehow because p-value is not intuitive in some sense. Okay, good. So what's p-value then? So that means after you collecting it, after collecting your data, okay, then you are going to using some statistics, right? Right here, using Z statistic, T statistic to do the testing. Okay, then basically it's you imagine is under your null hypothesis, your statistic T is going to behave or follow some distribution. Okay, and then by collecting your data right here, say this is T observation. Okay, after collecting x1 to xn, you calculate your T, for example, x bar. You calculate it. You using your x1 to xn to calculate x bar, and then you calculate right hand side probability based on distribution of T under null hypothesis. Okay, then that right hand side probability is your p-value. Okay, I think everyone knows that. And then in this class, I'm trying to show you one thing is why people using why be using p-value is valid. Okay, which means that it's if I'm going to using p-value smaller than alpha, smaller than type 1 error probability, then you're going to tell me that it's by valid means that it's an what? Label alpha test. Which means that it's my decision rule using p-value is a label alpha test. This is not trivial. Okay, when I say so, students say, "What is trivial?" Okay, this guy's smaller than alpha, the whole thing is smaller than alpha. No, it's not necessarily trivial. You need to pay attention to that. You need to show that to me. Whenever you're using p-value smaller than alpha, this decision rule. Again, this decision rule. Okay, against theta under null hypothesis, or maybe I should write it more clearly. Okay, you will say this is your delta x equals to 1. This theta right here belongs to null space. Okay, so if the p-value smaller than alpha is a valid test, then you need to show me that it's actually a label alpha test. Okay, so let's see some example right here. Okay, so if x1 to xn is random sample from normal theta 1, okay, testing about, theta smaller than theta 0, and then theta bigger than theta 0. Okay, say x right here is observed sample, right? You using x bar, which means again it's coming back to that graph I show right here. Okay, this guy is x bar right now, x bar distribution. Okay, this guy right here is your little x bar right here is your data. Okay, which means that it's p-value equals what? Probability under null hypothesis. Random variable x bar bigger than little x bar right here. You correct it. It's p-value. Okay, so that means it's right here. Oh, also you have to do supremum, right? I think you have to do supremum. Yeah, so yeah, I need to fix the slide right here. Okay, so the formal definition of p-value, actually, you need to put supremum right here. Let me take something out. Pardon me on that. Because your null space having a lot of points right here. So you actually want to do supremum because this basically the largest error you will make. Okay, good. But again, that's just saying it's okay. Let's not do evaluation right now. Let's say it's good things happen in the boundary. Okay. Hope you don't mind that. I say so directly. I can show you why it's the case by taking too much time. So I just will skip it right. Skip that. And then right here would be what? You just, in order to get this equation right here, is nothing but what? Just do standardization. Okay, because of normal 0, 1, I can 1 over normal 0, 1, 1 over square root n, then x bar minus theta 0, 1 over square root n right here. Okay, again, left hand side right here is z, normal 0, 1. That's the reason why z bigger than this quantity. That means 1 minus my CDF up to that quantity. Okay, that's the reason why you say that. You see that right here. Okay, good. So then this is my p-value. Okay, and then I'm going to say that it's like I said, I'm going to show that this is my decision rule, right? As long as you collected your sample. Okay, then right here. Okay, then this is my decision rule. That means I need to show that probability theta, then my p-value is what? My p-value is 1 minus v, then square root n, x bar minus theta 0, then smaller than alpha is going to become smaller than alpha right here. It's my target. Okay, so then it's not really hard to show that. Then let me just write it here. Maybe it's easier because you might. Okay, so let me another board. Okay, so I'll write down bios661 if I want to save it. Okay, it's 7th, right? Hopefully I get it right. Okay, so that means, let me do that, taking on. Okay, so that means, okay, oh yeah, okay, I forgot to check about chat. Maybe you guys have questions. I forgot about to check. Say, right here is that I'm trying to show that probability of p-value smaller than alpha. The goal is, this is my goal. Okay, the goal is trying to show that smaller than alpha because I want to convince everyone the using p-value to do rejection smaller than alpha is valid. Okay, so that means I can write down the p-value calculation I have, then root n, then x bar minus theta 0, then smaller than alpha. Okay, so then probably theta, choose theta. Then it's nothing but what? Nothing but move around. Root n, x bar minus theta 0. Okay, move around means that I move this guy to that right hand side, then alpha to left hand side. But remember, this guy's bigger. Okay, bigger than 1 minus alpha x. Okay, good. And then this guy right here, p theta. And then I do have I do need to use inverse function notation right here. That's 1 minus alpha, right? I want to move my phi to the right hand side, so I do need to using my inverse function. And then you need to know that which side doesn't change, okay? Think about it. Why that side doesn't change? If you don't know it, let me know. I'll let you know why side doesn't change. Then pretty much doing the same thing as what? Pretty much doing the same thing as we did all the time. We're trying to standardize it, then to get right here. Okay, and then let me see what else I need to find. Did I miss anything? Let me double check on that. Oh, yeah. No. X bar bigger than theta plus 1 over n. Yes, okay. Yeah, I think I'm good. So I just want to make sure that right here. Okay, again, I haven't put theta not yet. I said, well, it is a boundary, but I can actually evaluate. I think it doesn't take too much time of my time away. So if you do that, you x bar minus theta and then divided by 1 over square root m, trying to creating a new z's, and then theta 0, be careful, theta 0 minus theta, and then divided by 1 square root of n minus theta, and then this guy is plus theta inverse 1 over this guy right here. Okay, good. So this guy again is z. Okay. Then what we look at, again, I said by definition of the p-value is supremum under your null space. And your probability of what? Your probability of px smaller than alpha. Right? Good. So that means, of course, I want to evaluate whether or not that supremum happen in the boundary. Okay, which means that it's as long as my theta getting bigger, my whole probability getting bigger or not. If whole probability getting bigger, then that supremum having a boundary. The answer is yes, right? This is z normal 0, 1. The right hand side is a function of the theta. Whenever theta getting bigger, okay, the whole thing getting smaller. Okay, whole thing getting smaller, the right hand side probability of the normal 0, 1 of a normal 0, 1 is what? Getting bigger. So it means I can really feel safe about using theta not in a supremum. And then that means that I can plug in theta not right here. Okay, so that means that what I should write is z equal not, then not, then over root n, then plus phi inverse, then 1 minus alpha. Okay, good. Then become what? This guy becomes 0. Okay, then z bigger than something, it is what? Let me see. Z bigger than something, 0, it's 1 minus probability of z smaller than minus alpha. Just put equal to, how about that? It's fine. So again, z smaller than something, z normal 0, 1, that means 1 minus phi, then phi inverse 1 minus alpha. That means this guy cancel out, 1 minus 1 plus alpha, then become alpha. That means supreme of criteria using p-value smaller than alpha is actually what? Post alpha. That means the regular, or saying that it's only probability of any theta right here is going to be smaller than alpha, which basically is what we're looking for. It's a level alpha test. Okay, making sense? Okay, so this guy is nothing but what? Nothing but told you that it's, okay, p-value smaller than alpha as a criteria is a level alpha test. Okay, so it's a valid test. That means in general, this is definition of p-value. Okay, of course, you will null hypothesis only about, your null space only about single points. So there's no supremum you need to talk about. But right now, it's if actually null hypothesis only about single value, then just free to using that probability under null space theta 0, then this is distribution of your statistic. This is the data you collected. That's general definition of p-value. Any question on this? Up to here? Okay, no? So let me say something. I'm trying to talk to you about why people don't like p-value, and you don't necessarily like it, but it's a criteria of making decision. Okay, so what p-value actually means? P-value actually means that if your null hypothesis is true, how much evidence your data is going to support you. Okay, that's a frequent thinking. But actually, much more intuitive criteria should be what? Should be this. Actually, it's collecting your data, trying to evaluate how likely your null hypothesis is. Okay, so ask yourself, you like 1 or you like 2? I've told you, even I'm frequentist, I like 1, I like 2 better than 1. Okay, that's the reason why people would say is frequent thinking about hypothesis testing not actually making a lot of sense. Okay, but this guy still a good criteria to make a decision. Again, you can using any criteria to make decision. Some lousy ones, some good ones, any criteria. Okay, so even though frequent thinking about null hypothesis testing, not necessarily intuitive to Bayesian. Okay, but it's still good criteria for you to work with. Okay, of course, based on Bayes rule. Okay, I'll see clear Bayes rule. It's two guys do have connection, right? Okay, you could put either way. It's, for example, I can really writing down it. Probability of data, then probability of null hypothesis, intercept with data. And this guy right here could be writing down conditional PDF of this guy right here. If you treat every theta as random, like a Bayesian thinking is, these two guys definitely have connections. Okay, good. So you might hear people say p-value is not probability. Okay, to me that is p-value is actually probability, but it's not probability of null hypothesis. It's wrong thinking about p-value. Okay, good. But p-value to me is still probability. Okay. So, any questions on p-value? Okay, so if we began chance talk about Bayesian, then I'll keep talking about what's the Bayesian thinking about hypothesis testing and what's the frequent thinking about hypothesis testing. Okay, we could have even more in-depth discussion about two thinkings. So I think I'm following along. Thank you. Okay. Okay, thank you, Benji. Yeah. I mean, up to this stage, two claims, I mean, how do I say so? Two people still fight, okay? Bayesian Feng test, okay? But either way, our statistics. That's all I want to say. Okay, good. Let me use a final minutes talk about. It's quite important testing right now. Okay, I've told you that it's every time you told me which one is union intersection test or which one is intersection union test. I don't always get that right. Okay, by any means, it's nothing but logic game. Okay, what is the logic game is this? So sometimes we are going to test in whether or not I have to test in A or B. Okay, so imagine you are doing two hypothesis testing. Okay, if you want to have A and B correct, how to reject it? Right? As long as A or B wrong, you rejected your null hypothesis. Making sense? Okay. Another of testing is what? If I say my null hypothesis is A or B correct, in order to reject my statement, you got to tell me A and B are all wrong. Making sense? Okay. So one is union intersection test. One is intersection union test. I really don't know which one is which. Let's see which one is which. Okay. But that's the idea about union intersection test and intersection union. Okay, good. So the first one, I don't have time to talk about really detail. It's 44 right now. So how about I stop here? Okay, I'm going to talk about more about union intersection union test on Thursday. But again, it's really nothing but using your logic. If I want to reject it, if I say A and B both correct, how do you say I'm wrong? As long as you say A wrong or B wrong, right? If I'm going to say A or B are correct, how to reject me? You say both A and B are wrong, you reject me. Okay, so let's stop here. It's 1:44 right now. I wanna save some time for you guys. Any questions? Because I don't have, I cannot use in 1 minute to talk about everything right here.
Could you go back up to slide 28 just for a second? I missed some of that.
Yes. Mm-hmm.
Thank you.
Slide 28 right here. Yes.
Yep, that's good. Thank you.
Huh? Any questions?
I do have a question. So
yes.
When you were deriving the power for the two-sided test, you said that when data goes to infinity.
Yes.
And then
let me pull it out. I have that saved right here. Yeah.
So you kind of like divided it by the A section and then the B section. So when data goes to infinity, the A section goes to the probability of Z being greater than negative infinity, which is equal to 1.
Exactly, yes.
And then
Perfect.
B
Very good.
is Z is less than infinity, so that's also equal to 1. But when you add those two, you get 2 as your power.
Right, exactly. So that means one actually, so more precisely to say it's whenever theta goes to infinity, A part goes to infinity, but B part goes to 0. You see what I'm saying?
Part goes to 0.
Yeah. So, okay, did you follow me right here? You follow my pen, right?
Yeah.
You see my pen? Okay. So, okay, let's take out something not necessary. You are talking about good point because I did not mention that more specifically. You talk about both sides. So let me take all this. I want to keep that there. Okay, I don't keep everything right here. Okay, this is Z. So yeah, I should be more clear. Okay, again, this is A part, right? And this is the B part. Okay, So when you theta goes to infinity right here, okay, let me take that out and I want to be sure you follow my pencil. If theta goes to infinity right here, right? The A part, this guy goes to what? Minus infinity. Making sense? If theta goes to past infinity, then minus theta goes to minus infinity. That means the A part is going to become what? Z bigger than minus infinity. Then A part going to 1. You with me? You got it? Yes, right? But in the meantime, you also need to talk about B part. Right? If theta goes to infinity, it's not there. That's not there. It's Z. Sorry about that. I should put it here. If theta goes to infinity, the same thing. Okay? So this guy is a Z, right? Then the B part become what? Probability of Z smaller than what? Minus infinity. This guy goes to minus infinity.
Okay.
Right? So beta would be, the beta part actually is this. I should write this. I mean, I kind of lousy right here. I should write this. I should write this. It's your power function is going to become A plus B right here. Okay? So actually when theta goes to infinity, right? Then A actually go to 1, then B actually go to 0, then become 1. This is beta argument. Likewise, when theta goes to minus infinity, still A plus B, but A goes to 0, then B goes to 1. That's what I meant to say.
Oh, okay, I see. I got confused. I didn't see the little negative sign, so I saw that the probability summed to 2. So that's why I was confused. But it makes sense now.
Right. But you do need to talk about A and B part simultaneously. I sort of ignoring B part when I talk about theta goes to infinity.
Mm-hmm.
You know what I'm saying? I only talk
Yeah.
about A part, right? And then when I say theta goes to minus infinity, I want to talk about B part. Okay, I forgot to mention A part goes to 0 as well. That's my fault, right? But you want to make more solid argument, you should do A B part. You should look out A part and B part as well. Making sense?
Yes, it does. Thank you so much.
Okay, yeah, good. Any questions? If not,